for today. So we're going to talk about index tuning for the developer. This is basically going from level 100 to 200, something like that. We're going to talk about indexing and how you apply indexing on your environment. Now, for people who are a little bit more advanced in SQL Server, this will be a lot of repetition, but repetition is always good to maybe freshen up the knowledge you have on this. Okay. Now, who am I? My name is Stijn Wynants. I'm a Microsoft Premier Field Engineer like Fabian. I am from Belgium. And as I am Belgian, I am a very big beer and food lover, also chocolate, Belgian chocolate and specifically, and beer and food, yeah, anything with food and nutrition, I'm really into that one. But that's enough on me. Let's go forward with the agenda of today. So what will we be learning today? Because this is index tuning for the developer, I want to show you also some common coding mistakes, like T-SQL code that has been written in a way which doesn't allow your indexes to be used. We'll talk a bit more about that later, but it's going to be something on SARGable queries. Then we'll show you the difference between composite or single queries, single indexes. So what is the difference between them? Why is the one better or the other one better? In which cases are this one's good, the other one's good, all those things. Then I also want to speak a little bit about constraints and keys and why they are important inside your database, especially when you're going to join data. You want to make sure that those constraints and keys are there. And at the end, we'll see how far we get. We are going to maybe analyze a little bit the workload and see how your indexes are being used. Is that index useful? Can we drop the index? Do we need to create a new index? All those things. Okay. So after this session, we'll be able to tackle common coding mistakes, identify issues with indexes, analyze a query plan, and monitor your workload. So analyze a query plan, I think, is also really important. I hope all of you have ever seen a query plan. Normally, I would do a quick show of hands, but I hope everybody's raising their hand right now if I ask, has everybody here seen a query plan yet? Do we see any hands? I can't see anything.
Yeah.
Okay, good.
99%.
Okay, 99%. Okay. So we'll be analyzing query plans and basically just a few components which are related to indexing. Okay. Now, we first start off with the basics. Index types. There are different types of indexes. There are clustered indexes, non-clustered indexes, filtered indexes, Columnstore indexes. Those are mainly, and you've got hash indexes for in-memory tables. So those are mainly the main types of indexes you're going to come across. And most of the time, you're going to be working with clustered and non-clustered indexes. Now, clustered and non-clustered indexes are really like the main go-to types of your indexes. Now, to start off, what would happen if you would have a table with no indexes? That is called a heap table, which basically means you have an unstructured heap of data. I always like to compare this with the room in your house where you put all your junk. If my wife comes to me and she asks me, Stijn, can you go and find that book I had 20 years, let's say 5 years ago, it will probably be in the junk room. And if it's in the junk room, it's really, really hard to find it because the junk room is absolutely unstructured. It's just, I just piled all the data on there. So everything is there, but I don't really know where it is. So to get the data, I would have through that full room, pick up every item to find that specific book she was looking for, which will probably be all the way down and the last thing I pick up. So this is not really good, a heap table for fast data retrieval. But it is very, very, very fast for inserting, because if you need to put something away and you just put it away in your junk room, you can just throw it in. It's like, there it is. It's there. I don't have to worry about it. But it's really, really slow to get data out. So it's really slow to get that book out. And that's because of random I/O. Now, let me quickly show you here what that kind of looks like. Like in the time, everybody can see a whiteboard now, eh? Yes?
Yes, we can see it.
Okay. Like in the old school way of the disks, what would happen if you would go and get data from a heap table? So when we're inserting data, let's say this is our standard HDD disk from the old days. Okay. If we would go and insert data into a heap table, it's not going to be in a synchronous way. So we're not going to insert constantly to that table. So data might be here on the disk, 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 and all those things. And when we're going to read that data, what our disk is going to do is we're going to go and fetch that data like this. And this is called random IO. And this random IO basically means that we're going to go a little bit slower to fetch that data. To actually scan that full data, it's going to go slower. So that's why fetching that data from a heap table is really not the fastest thing to do. And also because it's unstructured, you need to read a lot of data to actually find it. Now, there's one thing I would like to point out over here, which is that row identifier. Basically, we still need to know what that row is we're looking for, and that is inside a heap table using a row identifier. It's for data retrieval. Now, what does this row identifier contain? It contains the file identifier, so it tells you on which file the row is which we're looking for, the page number it's on, and the number of the row on the page. Everybody knows what a page is? Can you see everybody understands what a page is, Fabian?
It looks like it, yeah.
Okay, so the page is the smallest item inside SQL Server for people who do not know what a page is, okay? So that way, using that row identifier, we're actually able to fetch those rows from a heap table. Okay, now, how does this look? It basically looks a bit like this. What you've got is your IAM page, your index allocation mapping, and this points to where the data is on those pages. And it's just going to have a header, and then the data is below it. Okay, that's the data structure of a heap table. Now, if you're going to fetch data, you're going to go to the IAM page, and then you're going to go to the pages to get that data. Okay. Now, how does this look in a query plan? It's really easy to see. Whenever I'm doing any performance tuning for a customer and they're telling me I've got issues with my performance, and I look at the query plan and I see this table scan thingy, and I see that it's a very high cost, that's one of the first things that click my mind, like, okay, we can do something about this. Probably there's a missing index or a clustered index that can be put into place to order that data. So we're going to fetch less data, which is going to increase the speed of and the performance of that retrieval from that table. And once we put a clustered index there, it's no longer a heap table, and it's going to turn into a clustered index table, which means the data will be structured. Okay. Now moving on. Let's say we don't have a heap table anymore. We're going to put a clustered index on there. A clustered index means the way your data is going to be stored, which means if we're going to insert data into that table, we will do it by ordering that data through a key value. It will order that data structure through a key value. This can be a single field key or a multi-field key, which means you can have like an ID, which is an integer, but you can also have the combination of an ID and, let's say, a date, for example. You never know why you need it, and it can be a combination as well. And this is in something called a B-tree structure. Now, a B-tree structure is actually a structure which looks a little bit like this. Let me go back here. Let's take a new whiteboard. You have here a page, which is actually your root page, and then go down here to your intermediate pages. Go, and then you have your leaf level pages. Now, if you would like to go and get some data, you will, for example, have an ID, which is your key value. And let's say this tells you this is ID 1 to 100, and then you need 1 to 50, and we're looking for value 45, which is on this page over here. And it will also contain your data. Your actual data will be in that leaf level as well. So if we need to fetch that data, we will go here, read this page, and then read this page, and then we have the data we need if we're going to look for ID equals 45. Okay. Now, this is very, very fast for reading data because it's in a structured way. This can be, if we're going to look at the disk again, it might cause you to do sequential I/O, because let's say we've got our disk here, data here. The data might be inserted like this over here and over here and over here, which means the data can be fetched like this, and like this. And it no longer has to go and do that way like the random I/O. It has more sequential I/O. It will still do random I/O, but it will be a little bit faster. Okay. Get a new one here. But it's fast for data reading, but there's an overhead to insert for the insert because we have to ensure the ordering. We have to make sure that if we insert data into a page, let's say we have ID 1, ID 2, ID 3, then ID 6, 7, 8, and we are going to insert ID 4, it has to be inserted in between the 3 and the 5. Okay. We have to ensure that that ordering is still there. This might cause something called page splits and all those things. We're not going to focus too much on that, but basically this means that you will have an overhead when writing data to that clustered index. Now this is how a B tree looks. You've got your index root page, and you've got your index rows, which will then have an intermediate level, which will then, like I just drawn, like maybe ID 1 to 50. And then maybe here it is 45 and the rows of data, which has the actual data. Okay, so this is basically how it works. So if you've got a clustered B tree index, you got your pages and you're going to hop through all these levels to go down to your data level and fetch your actual data. Okay, this is how a clustered index is built. It's called a B tree. Okay, the less hops you need to do, the faster your index will be. Now, if you're going to see in the query plan that you're reading from a clustered index and you're scanning the data, basically this means that you're going to read everything from that clustered index. You will see something like this, which is a clustered index. And yeah, you can't see this thing here, but it should show you scan. Okay. Now, moving on, we go to the second type of index, which is a non-clustered index. Now, a non-clustered index is not the way your data is going to be stored. You've got two types of indexes with the way your data is going to be stored. It's a heap table, which is using the row identifiers, or a clustered index tables, which is using your clustered index key as the way your data is going to be stored. Now, a non-clustered index is always an additional way of storage, which means it's an additional storage, which means it's an extra overhead when writing data to that specific table. Okay, the non-clustered index at the leaf level. So at the leaf level, that's the lowest part of your index, of your B tree index, will always have a reference to the row identifier or the cluster index key. It would be a row identifier if the table is a heap table. You can put a non-clustered index on a heap table, but you can also put a non-clustered index on the clustered index table. And if you're going to put it on a clustered index table, then you would have a clustered index key. As I told you before, this will have an additional overhead for writing because you don't only write the data once to the heap or to the clustered index, but you will also have to write to the non-clustered index, which means you're doing twice the amount of data. You're not exactly twice, but I'll show you later how much overhead it's going to be. And you also have an additional overhead for memory. Why is that? Because if you're going to read or write data, you're always going to go through the memory. And if you're going to the memory, if you're going to read data from your clustered index and then read data from your non-clustered indexes, both objects will be inside memory, which means you will have two times the same type of data, the same table inside your memory, which can cause overhead to your memory as well. Now, this is how a non-clustered B tree looks. It looks about the same as a clustered index. The only big difference is in this part over here. This will not contain all data. This will only contain the data you specify in your include column. And a little bit more on include later. But basically, if we're going to look for a value here, let's say we're looking for an apple. And we know it's going to be from A to Z here, and then A to B values are here, then we know that apple is here. And then we only have the value apple. So if we then need to have the actual row value, so all other values from that table, and those are not included in the index, what we will have is we have the clustered index key or the row identifier, which we will then use to go to the other index, to the clustered index, or to the heap table to actually fetch the data. Okay. What does this look like inside the query plan? It says index scan. The previous one would say clustered index scan. Okay, that's the main difference. Any questions so far?
Not so far now.
Okay. Is the screen readable, or do I need to zoom in?
It's readable, yeah.
Okay, good. Now, next to the non-clustered index, you have got include columns. While a clustered index has all column values in the leaf level of the B-tree structure, a non-clustered index by default only has the row identifier or the clustered index key in the leaf level. Okay. Now you can add additional columns inside the leaf level of a non-clustered index, and that's by using the include part of the create statement of your index. And this can be used to add columns which are for specific queries. Let's say you have a query and you're going to select the price and the type of fruit, and you've put an index on the type of fruit. Then you don't have that specific price inside your non-clustered index. If you would then include the price, then it will be included in the leaf level, so which means the bottom level of your non-clustered index, and you don't need to go and fetch the data from your clustered index or from your heap table. Okay. Now there's something else which we call covering indexes, and covering indexes means you're going to create an index that covers the full query. What I see a lot at customers is people who then include every column field, which means you just doubled the amount of data you have, which means if you have your clustered index on the specific key and you've got all your values in the include column, and you've got all your values already in your leaf level, and you're going to then add a non-clustered index and add all columns which you don't have inside your key values for your non-clustered index inside your include level. It's going to include it also in the leaf level, which means if you're going to write one row, you're actually writing 2 rows. If you then add a third index, you're going to add 3 rows instead of 1 row, which means the overhead for writing data really goes up exponentially. We'll see that later in the demo. Now, if we don't have these values inside an include column, we're going to do something which is called a bookmark lookup. Now, what is a bookmark lookup? A bookmark lookup means we're going to fetch using the row identifier or the clustered index key, depending if it's a heap table or if it's a clustered index table. We are going to fetch the data from the clustered index or from the heap table structure to get the data. Now, if we're going to data fetch from a heap table, it's going to be called an RID lookup. And what is going to happen with an RID lookup? Inside the non-clustered index, we will find the row identifier, which contains the file ID, the page, and the number of the row number it's going to be on the page. And we're going to directly go and find that page. Okay. If we're going to have a key lookup, we're going to fetch the data from the clustered index. Okay, so what happens here is we first are going to go through those intermediate levels, and then we're going to go to the leaf level of that index, which means in this case, you will probably do more reads. But because you don't really know the structure of this, a part of the row might be on another page. This is called a forwarded rec. And that can really hurt your performance as well. If your data is really inserted, really structured, the RID lookup might be faster, or the key lookup will do more reads. But if you have more forwarded recs, the key lookup might be faster than the RID lookup. But basically, for me, RID lookups and key lookups might usually be not a very good thing for your application, and it really can make or break your application's performance. It's good when it's a very small amount of data you need to go and get, but it's really bad when it's going to scan about 20, 30,000 times for that key lookup or the RID lookup. It's really going to hurt your performance. For example, if your statistics are out of date and you're expecting to get 1 or 2 rows, but it actually is 100,000 and the plan has chosen to do that bookmark lookup, you're not in for a fun time with your application. Okay, you might get timeouts and stuff like that. Now, how do they look? You've got your index seek here, which is your non-clustered index, and then a key lookup, which is then going to be a nested loop, and then you're going to present your results. Same thing for a bookmark lookup. You have your non-clustered index you're going to use, and then you're going to do a RID lookup of the heap table, nested loop, and then a select on it. Okay. So let me show you how that works. Go to my SSMS. So I'm connected here to an Azure SQL database, a database called Real-Time Analytics. Don't really mind too much about that. And I'm just going to drop and create a new table. So I'm going to create a table, which is called DBO Heap Table. I'm going to have an int identity here and some value, which has a char 1000 here. Now, quick question. Who uses int identity like this? And can somebody tell me what might be wrong with using int identity like this? I always like to know if somebody knows what's wrong with the int identity statement as I've put it here. Anybody?
Doesn't look like it.
Okay, so the main issue here is, what's the range of an integer? It goes to minus as well. So basically what I just did is I threw away half of my integer range. In 99% of the cases, it's not going to be a big issue, but if you're going to need those extra 2 billion rows or something like that, you will need that to start it with minus 2 billion, blah, 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 to actually have all the range of your integer. Okay, that's something I learned from a guy who codes a lot and who had that issue once. Or otherwise, if you're going to have too many rows, you need a big int. Okay, so that's a small thing in between. Anyway, I'm just going to create a table. Oh, press the right button, Stijn. There we go. Create a table, and it just contains like a very large column and an ID for identity. And I'm going to insert 100 rows. Okay. So let's wait a few seconds for this thing. Insert. Okay. Now I'm going to turn on my query plan and statistics time and IO on. What does this thing mean? This is going to tell me how much time did the CPU spend to actually execute that query, and IO means how many rows have how many pages have I been reading, and forward recs and all those things. So what I'm going to do now is I'm going to turn on the query plan. I've already done that, and select from that table. As you can see here, the execution plan we get is what we've seen before: table scan heap table. So that's correct. And if we're going to see here, you can see that we have a scan count 1 and 22 logical reads. Okay. Let's just store this for a while. Let me grab my pen. It's dark here now. I can't find my pen. Okay. Let's just write. Oh, where's my pen? Okay. I'll just write 22. Can somebody write down 22 somewhere over there? Let me know if it's written down.
Yeah, I got it, 22.
Okay, 22. Okay, now I'm going to drop and see if the table exists, a clustered index table. I'm going to create, you see, it's the same table structure. Okay. And I'm going to create a clustered index on it. Turn off query plan as well. And I'm going to insert 100 rows again. Now I'm turning on the query plan again and executing this query. If we look at the execution plan here, we can see that we have a clustered index scan. Okay, 100 rows, we're scanning that data. Now, what happens to the amount of IOPS we're doing? As you can see here, now we only have 17 logical reads. It's because it's well structured, that data. And a heap table is going to have more of a sort of overhead when looking at the page. It's going to reserve more pages, read more pages than it actually needed. Which means with your clustered index, the data fetching of a clustered index is already going to save us a certain amount of data. Just don't look at this at those 100 rows we've inserted, but look at 1 billion rows. It's going to make a significant difference. So we went from 22 to 17. Can you write down 17?
Okay.
Perfect.
I got it. 17.
Perfect. Now I'm going to drop a table, which is called non-clustered index table. Same table, as you can see, int identity, some value. Okay. And I'm going to put the non-clustered index on some value. Okay. I'm going to put ID and include some value. Basically, what is this? Can you tell me what this is? Something I've just told you before. It's called a specific index. If you include every column field inside your non-clustered index.
Type of index.
Covering index, indeed. Okay, let me see if I created it. There we go. And now I'm going to insert 100 values again. Okay. Will this be the same amount of rows if I'm going to execute this here? So here we see it's an index scan. The amount of pages we're going to fetch here is 17. And if I'm really clear, it should be the same as a clustered index, no? $17 was, I think it was the same. Yeah, should have been the same.
It was the same, yeah.
Okay, so basically it's also a B tree structure and it also has all fields in there. So it's going to be the same amount of it's basically a clustered index, which we created as a non-clustered index. Okay. Now, I'm going to show you the bookmark lookups and the impact that one has. So what I'm going to do is I'm going to create a table called DBO bookmark lookup with an ID, some value, and some value 2. So some value 1 without the 1 has char 1000. Some value 2 has a varchar 100. Okay. And now I'm going to create a non-clustered index on it. So a non-clustered index on some value. Okay, which is this specific column. Okay. There we go. And now I'm going to insert first turn off execution plan, because otherwise we'll be in a heap of trouble. And I'm just going to insert 10 times A and B, 1000 times B, and 1000 times C and B. Okay, what I'm actually creating is an inequality in the amount of data we have inside that table, which means we have a lot less of A and B than we have of B and B and C, or C and B. B and B will have 1000 values, C and B will have also 1000 values, while A and B will only have 10 values. Okay, let's go 10 means execute this 10 times. Okay, let's wait for this to execute. Just a few more seconds. Might have wanted to turn this off. Just a few more seconds. I'll just stop it. It should have been enough. Let's make sure that we insert those values as well. There we go. Okay, and now I'm going to select from those 10 rows. So I'm going to go and select from bookmark lookup where some value is A. And include the plan. You can see here, we have an index seek and a RID lookup. That RID lookup, look at the cost, is 88%. So basically that's a very costly operator. It's seen inside the query plan as a costly operator. Okay, and then here the index seek is 12%. But now let's look at the amount of reads we've been doing. So the bookmark lookup does 18 logical reads. Can you write down 18 again?
Okay.
That's all we have here. Okay. Now I'm going to create a clustered index on ID. Okay. Now I'm going to do the same thing, same query as you can see here on some value, and we're going to use that non-clustered index again. Okay. And now I'm going to execute that again. So same results. As you can see here, now this has changed from an RID lookup to a key lookup, and it's an index seek, and it is 89% the cost. Okay, now looking at the messages, the amount of reads is 26. So who remembers why this is more? Why are these reads? Why are we doing more reads? Let me know if somebody has an answer.
Someone was saying because it needs to be read double the time.
No, it doesn't have to read double. What you have to understand is we're going to do with that key lookup, we have to go and through those intermediate levels as well. Well, previously with the RID lookup, we just go to the page where the data is. Now we have to read the clustered index. So the 2 hops of our clustered index are 2 extra pages we're reading, and that's what we see here in those 26 logical reads, which means it's a little bit slower than the heap table, but it's because the heap table is now very structured. It's inserted data in a structured way, so it is kind of structured inside our database as well. If you're going to have a very big table, that heap table will be small. It will be a lot slower. Okay. Now we can also just create a non-clustered index, which is covering, because we're going to include some value 2 here as well. And now see what that does. If we look at the execution plan, now we get an index seek, which is good. And if you look at the messages here, you can see that we are only doing 6 reads. So we went from 26 to 6 or from 17 to 6. So basically a covering index for this query would be the best way to do it. But we have to remember that we will have to have an overhead of writing the data to those tables, because we will double the amount of writes we're doing because we've doubled the amount of data we have in that table. Okay. So any questions on the previous part?
Not so far.
Okay, good. I've got a question slide, but so that was a bit on the basic structures of an index. So what is a clustered index, heap index, a heap table, what is a non-clustered index, what's include, what's RID lookup, and now we're going to step it up a notch and we're going to go through the common coding mistakes. So I have put an index on my table, and why am I not using it? So what is the reason why I am not using that index? And that's because of something called SARGable queries. This means search argument able queries. Now, what are search argument able queries? If those are non-SARGable queries, we're not going to be able to use an index because we've made a few mistakes in our coding. One of the most common mistakes I see is functions in the where class of the data field, which means if we're going to go and search for the year, that's a very common one I see. Let's say you're going to select the data from a table where year, the date, equals 2019. So we're going to put a function on that date field. What happens is it first has to go and scan all the data, and then it will give you, then it will filter that data after it has scanned everything, which means we are not using the index to seek the data and have less IOPS. We're actually going to read everything and then just filter it at the end, which means it's it's more resource intensive because we're still going to scan it. Also, something you see very frequently is calculations in the where class of the data field, where you're going to say where price is price plus tax equals 15, for example. A calculation, if we're going to combine 2 fields in our where class, what happens if we first have to scan the data, make that aggregation, and then only give back the data? And how do you solve this? It's actually by rewriting your data a little bit, rewriting your query a little bit. I know a lot of you will not be able to rewrite the queries because you might have software or something like that which you're getting out of the box. But if you're going to create queries yourself and you keep in mind SARGable queries, you will write a lot better code and you're going to make a fit for your indexes, which will increase the performance of your application. Now, non-SARGable queries, let me just put it very clearly here, non-SARGable queries. This is an example of a non-SARGable query. Everybody, I think a lot of people have used this. Where is null equals null, okay? This is not a good practice to do because what we will have is a scan, okay? Where left some field, comma 1 equals A. We'll also do a scan. Where product ID, which is defined as varchar, equals 12, which is an integer. This will also cause a scan because we don't have the same data types. It's called implicit conversion. Oh no, that's something we're going to see later. Basically, this means that we need to make sure that if we're going to learn this product ID, we have to make sure that the varchar and this is varchar, okay? It has to be the same type of data. Another example, where product ID defined as a varchar is compared to an n-varchar. It's also going to scan your data. This is called implicit conversion. Okay, it's going to scan. Where a calculation here, unit price is less than 100. Okay, this is also going to scan your data, and it's going to be non-SARGable. So these are all mistakes we can write. Okay, and then also this one. This one is always a lot of fun. Where like %%A. This is always going to scan your data, and it's always going to hurt your performance. It's really not a lot of fun to do that. Okay. Now, what are the solutions? So this one was the bad one. Is null, comma some field, comma 0 equals 0. What you can easily do is where some field is 0 or some field is null. It's the same query, but this will scan and this will seek if you have an index on some field. Where left some field equals A, this will scan. While some field like A%, that will seek, that will be able to use an index on some field. Where product ID defined as varchar equals 12 will scan. Well, the product ID defined as varchar and you then do it with those quotes, that will seek because the data types are the same. Product ID defined as varchar and with a non-unique code, if you just do it the same types, you will get a seek. Where unit price times unit price is smaller than 100, you will have to use something called an index computed column. And this is actually a trick I found online. I think it was Aaron Stilato I found it from. It's really Aaron Stilato. I'm not sure if it was Aaron Stilato. It might be somebody else. But basically, it's a really, really cool trick which you can use to actually make a calculation which is in the computed column, and then index the computed column, and then it turns that scan you have into a seek. Pretty cool. And then we're looking like a value like this. You should try to reduce the usage. And if you're looking for full words, you might want to use a full text index. Or what you can also do is when you're going to do like a value like A, make a smaller index for it. A smaller index, which is actually a little bit of a thinner index, which means you're just going to have some value and, for example, the clustered index key in there, and then scan only that, and then have a predicate on it to only get the keys you really need, and then go and seek those key values, which will do less I/O than if you're going to scan that full table and all that data. It might increase the speed. It will not definitely increase. It will not be a guarantee to increase your speed. Basically, %% is one of the hardest things to solve inside SQL Server if you have performance issues with that. Now let me show you what the impact is. Okay, I grab my second demo. So I'm going to drop a table called SARGable queries, and then you're going to see that I'm going to create a table where ID is int identity. I'm just going to quickly change my connection. I'm going to use my local one, which is going to go a little bit faster here. So create a table with ID, which is a primary key, some value, which is a varchar field, some value 2, which is n varchar field, price, which is an integer, unit price, which is an integer. Okay. First, I'm going to insert A, B, 1, and 2, and I'm going to insert that 10 times. There we go. And now I'm going to insert C, D, 2, and 3 1,000 times. There we go. I'm going to create a non-clustered index on some value, which is this n varchar field. And I'm going to create a non-clustered index on some value 2, which is the n varchar and the varchar. Okay. Turn on query plan. Now, first one is the bad query. Let's just show you statistics times and the query plan. Okay. What happens if I do this here? What we get is we get an index scan. Okay. Using that is null. Looking at the amount of logical reads we're doing, it's 4. Okay. It's not a lot because I don't have a lot of data in here, but basically this is a scan of that index. Now, what happens if I'm going to do where some value equals A and some value is null? We get here is we get an index seek. which means this index seek is going to do less reads. We're only we have 4 reads, of course. I've done something wrong here. I think I haven't inserted enough rows. But basically, this means that here, which is exactly the same query, exactly the same result, we're going to do an index scan here, which means we're going to scan the full table, while here we're just going to fetch the rows we need and have an index seek, which is going to be better data fetching, which is going to be faster and more scalable. Okay. Same thing here, when I'm going to select where left some value equals A. Execution plan, you can see here that we're scanning the full table again. Well, if we're going to do it like this, it's the same query. Did I get results here as well? I got results here. Am I not doing something? What have I done? Basically, it can seek here, but I should have gotten
missing the like. You have an equal instead of a like.
Ah, yeah. There we go. Good that you're awake, Fabian. Thank you. It's been a long day. As you can see here, same result, and then here we have an index seek. There we go. Then, same thing here. If we're going to do it like this, we have an index scan. And what you get here is a nice warning sign. It will tell you here, convert implicit and varchar might affect seek plan in query plan choice, which means this value, if you hover over it, is varchar. Well, this will be non-Unicode and varchar. If you do it like this, it will go back to a seek and you're rid of those nasty warning signs. Okay. Then this one is a little bit more complex. So select ID from SARGable where unit price plus price is lower than 4. If we're going to select this, it's going to do a clustered index scan. It's going to scan the full table. Now, is there a way to get this a little bit faster? What we're going to do is we're going to add a computed column like this. You can see here, add C price where unit price plus price. And then we're going to materialize that computed column by putting an index on there. As you can see here, I'm putting on a non-clustered index on that C price. And now I'm going to select the ID where unit price plus price equals 4. And what happens, we now get an index seek, which means our calculation in our where class now gets turned from a scan to a seek, which is more efficient, which is faster. So if you have those calculations in your table, in your queries, it might be good to add a computed column and put an index on there. So basically, if you keep these things in mind, you're going to write a lot better code and hit indexes, which will allow you to speed up the performance of your application. Any questions on that? Nope.
There is one question.
Yes.
Someone asked what's the performance impact of having the calculated column with the index on it?
It's an insert.
Yeah.
It's an insert at runtime. So if you're going to insert the data, insert is going to be on the computed column as well to the index. And if you're going to have an update, it's going to be an update against that computed column as well. Extra overhead for writing and updating data. Okay.
Okay, thank you.
Now, the next part, index ordering and composite keys. Now, what I'm going to show you here is what happens if you have multiple small indexes versus a composite index, so an index which is a combination of different types of fields. Let's say you've got field A, B, and C, so 3 different fields, and you're going to put an index on A, index on B, index on C. You can also create, for example, a composite index on A, B, and C together. And why you should use which one and in which cases I will show you later. This is also something very good to look for redundant and duplicate indexes. Who here has ever applied a missing index detail? I have raised my hand myself because I do it constantly. I think everybody has done that.
Close to
everybody.
4 hands go up, but close to everyone, yeah.
Okay, so basically everybody has done that, and if you haven't done that, I would think it would be very, very brave of you if not ever doing that. Now, what happens is if you do those things, you might get redundant and duplicate indexes, which means you've got an index on value A, then an index on value A and B, an index on value A, B, C, an index on value A, B, C, D, and then include with E, for example. So basically a lot of duplicate or redundant indexes. Redundant means you're using the same type of fields, same amount of fields, the same time for the same index. Okay, which is causing overhead because you're going to have to insert in all those indexes as well. And now the most important thing with those composite indexes is the way you order your index. If you're going to create an index and you're going to create an index on A, B, C, it's a different index if you create the index on C, B, A. Okay, and I'll show you what the impact is on that. So let's go back to the demo board. And let's open up the next one, which is called Composite and Index Ordering. So I'm going to create an index here, quickly drop and create it. And I'm going to insert 200 rows 1, 2, and 3. There we go. And I'm going to insert 2,500 rows of 4, 4, 4. Basically what this is, Ger 500, Ger 500 is all IDs. Okay. And now I'm going to create an index ID where I include ID 2 and 3. Okay, do that. I'm going to create an index 2, which is ID 2, which includes ID 2, ID and ID 3. Index 3, which is ID 3, which is ID 2 and ID 1 in there. So basically we've got indexes on everything. Okay. So if I'm including my query plan here and we're going to find data on this, so what you can see is we have ID 1, ID 2, and ID 3. And we're selecting on that. So ID 1 has to be 1, ID 2 has to be 2, and ID 3 has to be 4. Okay. If we look at the execution plan, we get an index seek, and which index are we using here? So you can see here we're using index 1, which is doing a seek, and our seek predicate is on ID 1. Okay. And afterwards, we're going to apply the predicate of 2 and 4. We're going to see at the messages, we can see that we have done 74 logical reads for this query. Okay, let me drop those indexes now and see what happens if I create a composite index out of that. So I'm going to create a composite index on ID 1, 2, and 3. And I'm going to do exactly the same query again. As you can see here, I get an index seek, of course, on that composite index, as you can see here. Where is it? Here we go. Compix, that's the composite index I made. And if we're going to look at the amount of reads I have, we only have 8 reads, which is a lot better. So in this case, a composite index for this specific query was a better choice. Okay. Now, moving on, if we keep that composite index, what impact does it have if we change that query? So let's say we're going to go and fetch data from ID 1 and ID 2, but we're leaving out ID 3. Okay, we do that. So you can see here what happens if we get 54 logical reads, but we still get an index seek. Okay, get an index seek because that composite index is built ID 1, ID 2, ID 3, which means ID 1 and ID 2 can be sought on. Okay, you can see here, we get is seek predicates on those two. Good. Now I'm going to do where ID 1 is 1 and ID 3 is 4. We get in this case is we get our execution plan. We're here. Oh, fast. Go back here. Our seek predicate is only on ID 1. And then afterwards, after we've done our seek predicate on ID 1, then we're going to apply the next predicate, so sort of a scan on ID 2, ID 3, because ID 2 is in between of ID 1 and ID 3, which means we cannot seek on ID 3 as well. Only if we've included ID 2 in our where class, we will be able to seek on the full index. Now we're only able to seek on the primary, the ID 1. Okay. Now what happens if we're going to select from ID 2 and ID 3? Then we're going to scan the data. This is because the index was built ID1, ID2, ID3. If we would have created it ID2, ID3, ID1, we would be able to seek on it. But that's not the case. We're selecting for ID2 and ID3, which means we're not going to be able to add that predicate, that seek predicate. If we check here, we first have a scan, and then we're going to apply the predicates on ID2 and ID3. So which means that we are not able to use our composite index anymore. Okay, so when looking at your data and looking for those composite indexes, make sure that you find the queries which are using it, and make sure that it's always a combination of those 3 fields or those 4 fields, and make sure that the first field you have in there is always included inside that where class. If it's not included, you will be in a world of trouble, because then you start scanning and your indexes just ceased working. Okay, any questions on that?
No.
Okay. So the next part I wanted to talk to you about is constraints and keys. Now, constraints and keys are basically sort of a nerve system inside your SQL Server database. So primary keys and foreign keys can reduce the amount of joins that need to happen inside your SQL Server query. Let's say you've written a query where you're going to select ID from table 1, which is the primary key. And you're going to say a join with table 2, and you're joining on the foreign key there. If the foreign key is trusted and you're selecting data on it, it's not going to look for that foreign key. It's not going to make that join, because it already knows, because it's trusted between them, that that data will exist in that other table as well, so it will not do the join. If it is not trusted, it will still do the join and do a lot more IOPS. Okay. Also, constraints can reduce the data retrieval. For example, if you put a constraint on it and you know that that value is going to be unique, or that value is, for example, always going to be more than 2, and you're going to select the data where data is lower than 2, you know that there's no data going to be retrieved, so you're not going to scan or actually go and fetch the data from the tables. Okay, let me show you how that works. Go and get the next one. So I am on the right one. Okay, there we go. Include actual plan. I'm going to use AdventureWorks here. And what I'm going to do is I'm going to here go and get from sales order detail, and I'm going to join with sales order header on sales order ID. As you can see here, those 2 here. Okay, and if I hover over this one, you can see that this one is the primary key. Okay, and this one is also the primary key in the other one. Okay, now what will happen if we've got the plan here, if we are going to execute this query, as you can clearly see, we've done an inner join here. We check the execution plan, we're not going to fetch the data from the other table. Why is that? Because we're only selecting the column values of the SOD table, which is this table. And there's a trust between these between that table and this table, which means we don't have to go and fetch the data there, because we know it exists between them. Okay. Now, the next one. What I'm going to do now is execute this query, where I'm going to do where sales order header, sales order ID is 43,659. As you can see, now we're going to do that join. Why? Because we're actually referencing something from the other table. If we're referencing something in our select or in our where class from the other table, we're going to access both tables. Okay. Now, if we're going to do this one here, basically this is select SOD all order tables, so we're selecting everything from here, from sales order detail, and exists. See here, and exists, select star from sales order header. So we're not doing a join, we're doing an and exists. We're doing that query. So you can see here, it's also not going to fetch data from that table. So we're skipping that join. Now you might ask yourself the question, why do that join in the first place? You would be amazed how many people write those queries or use views which have all those joins in there, and they're just always selecting from those specific views, which means if you have those queries and those views in there, and you're actually joining on those primary and foreign keys, you might reduce the amount of joins needing to happen to actually get that query. Okay, now what happens if we untrust that one? So remember here, if you can see here, alter table, no check constraint. So which means I'm going to uncheck that constraint, that foreign key will no longer be trusted. We then do the same query again. As you can see now, an untrusted constraint will force this, because that foreign key is no longer trusted, we will have to actually go and get the data from both tables, which is a lot more data we have to go and get. Now, if we want to check this again, we execute alter table with check. It's always one of my favorite statements in SQL Server. We're not going to check it, we're going to double check it. So check, and then the constraint is trusted again. And if we then execute the query again, it's this one. As you can see, it is not going to get the data from the other table again. Now, this one here, let's say we're going to execute this query. What is going to happen? We're not going to access any tables. We're going to look at the execution plan here. No table was accessed. Why is that? Because we have a constraint on the table, sales order details, on unit price, and unit prices always have to be positive. So if you're going to look for a negative price, we're not going to find that because that doesn't exist. Okay, so that's the way constraints can be used to reduce the amount of joins. Okay. Any questions on foreign keys or constraints?
Nope.
Okay. How much time did I have for this session? Was it 1 hour or is it a little bit more?
It's 1 hour, but I can make mine a little bit shorter.
No. I'll just quickly show you one more thing, and you can choose what we're going to see. Okay. Nope, discard. So what else can I show you? Having too many indexes, redundant or duplicate indexes, or index uses statistics. What do you want to see of these three? Who wants to see too many indexes? Quick show of hands.
4, 3-ish,
Okay.
4.
Okay, redundant or duplicate indexes?
3.
Okay, index uses statistics?
42.
42, okay. Good, we'll look for index uses statistics then. So, oh, wrong button. 1 second, go back here. Come on, don't crash now. There we go. Index uses statistics, slideshow from current site. That's going to be better. So there is a DMV, which is going to show you the index uses statistics since the last time your SQL Server was booted. Now, what is this one very handy for is it can show you if your indexes which you've created and put a lot of time in, if they're being used or not. Now, what you want to look for when analyzing the data of index uses statistics is look for indexes with only updates. If you're going to use an index, you want to make sure that you're actually reading from that index and not only keep maintaining it, which means only updating the data. So if you see an index which only has updates of, or let's say you've got 2 million updates and 3 seeks, it might be possible that you don't need that index. Of course, you always have to check with the workload, and maybe it's a very, very critical query which runs 3 times a month, which has to go really, really fast. But apart from that, that might be a good case to actually drop that index and reduce the overhead in writing the data to your table. Also, look for indexes, which has no seeks. If you have an index with no seeks, you're not really using it. And also look for indexes who have a lot of lookups. If you have a lot of lookups, it means that you maybe need some include columns, which means some other indexes might not have all fields in there. So you might want to start using some index included columns. It's not always possible, but it's a possibility to look at. Okay, now let me show you the DMV. The DMV I want to show you here is index usage statistics. Seconds. There we go. This is the DMV. it's from this website. I'm also going to share everything here, all demos, and also the other 2 demos which you haven't seen. You can go and execute them. Normally they've been they should run on every system except the ones with AdventureWorks. Now, like, look here to SQL Shack, gathering SQL Server index statistics and usage information, and it's going to focus itself on DMDB index usage stats. Okay, what is this going to show you? Here we go. For each index, the size, well, this is the sweet thing here. You're going to see the number of seeks you had of that index since the last restart of SQL Server, the number of scans, the number of lookups, and the number of updates. As you can see here, this clustered index is really good. And let me look for one which is not that good. I don't really have one which is not that good at this moment. Let's see. Let's say this one, for example, has 16 scans and 9 seeks, which means we're scanning too much and not really seeking a lot. Or this one here has updates, but no seeks or only seeks and scans, which means no seeks, scans, and updates might be a good one to drop. That index is not really being used, so we might have a better index. And usually what you can see in those things is you will probably get another index which is being used a lot for seeks. You might want to create a clustered index from that non-clustered index which is being used a lot for seeks, so you reduce the amount of lookups for other tables and all those things. Okay, that's basically in a nutshell index user statistics. Just play around, run that query on your system, and you can really find a lot of stuff on there. Basically what you want to do is maybe then change the query a little bit and order by, let's say, user scans. No, user scans here. Just quickly grab this one out. Then you can see, okay, this one is being scanned a lot. What's happening and all those things. Okay, or where, for example, the seeks are 0. Okay, so that index is not being used. Now this is because my server restarted like an hour ago. We're not going to see a lot of data in here, but basically this is a very good DMV to work with. Okay. Now, summarize index types. Remember, we've got all these different type of indexes. We've got clustered indexes, non-clustered indexes. I haven't really touched upon filtered indexes or clustered Columnstore or Columnstore indexes. I have another session on that. If you ever want to see that, I'm happy to give that one. Bookmark lookups are evil, so if you're going to get data and you need those include columns, make sure you find and not have too many bookmark lookups. If you have too many bookmark lookups, you will have a heap of trouble because you will have to, it will really slow down your application. SARGable queries are really important, so make sure you write your codes that you can hit those indexes. And also don't forget that your index ordering really matters. If you are having an composite index with ID1, ID2, ID3, and you're searching on ID2, ID3, it will not be able to be used. Constraints and keys can reduce joins. Don't over-index. You can check that in the query, in the demo I have there, and check your index usage statistics so you know that you're actually going to use those indexes or not. So, any more questions?
Any questions? No, not so far.
Okay, then I would say thank you very much for listening, and I would love to hand over to Fabian, who is going to blow your mind on partitioning.